Across the cosmos, most of what shapes the fate of galaxies is invisible. Dark matter quietly binds galaxy clusters together, while dark energy drives space itself to expand faster and faster, stretching the universe over billions of years. Together, these two unseen ingredients control the large-scale future of everything we can see. If you enjoy calm journeys into the mysteries of the universe, please subscribe and share, and tell us in the comments what confuses or fascinates you most about dark matter and dark energy. Thank you for watching. Now let's begin. Matter in the familiar sense is only a small part of the story of the universe. Atoms, stars, nebulae, planets, gas clouds, dust, oceans, mountains, cities, and living tissues all belong to the same category of ordinary matter, built from protons, neutrons, and electrons that interact with light. Telescopes across the world and in orbit count this luminous content, measure its motions, and estimate its mass. From these measurements, cosmology builds a kind of inventory of everything that exists on the larger scales. In that inventory, the bright part that is easy to see turns out to be a minority share. Calculations based on many independent observations indicate that all ordinary matter adds up to only about 5% of the total cosmic energy budget. The rest belongs to components that do not shine, do not absorb, and do not reflect light in any direct way. About 25% appears as dark matter, an invisible form of mass that reveals itself through gravity. About 70% appears as dark energy, an unknown form of energy linked with the expansion of space itself. Together, these two dark ingredients dominate the evolution of the universe from its earliest times to the present era. The idea that ordinary matter is only a small fraction emerges slowly from decades of work, rather than from one single experiment. Astronomers study the motions of galaxies in clusters the way stars orbit in their host galaxies, the pattern of temperature variations in the cosmic microwave background, and the large-scale arrangement of galaxies across billions of light-years. Each method offers a different way to weigh the universe. When the results are compared, they form a consistent picture in which the familiar matter that builds stars and planets cannot account for the gravity that is observed. The numbers converge on a cosmic recipe in which every galaxy and every cluster sits inside a much larger dark environment, and the expansion of space responds to a smooth background of dark energy that does not clump or gather in the same way as mass. Ordinary matter behaves in detailed ways that are well tested in laboratories and in space. It interacts strongly with light. It forms atoms and molecules. It cools, collapses, and fragments into stars, planets, and gas clouds. This behavior leaves a clear signature in observations, so the amount of ordinary matter can be inferred with some confidence from the brightness of stars, the content of gas, and the detailed structure of the cosmic microwave background. When the total mass that gravity seems to demand is compared with the visible share, a large gap appears. That gap is the first statement of the dark sector, a simple mismatch between what is seen and what is required to explain motion and structure. Dark matter and dark energy are introduced to close this gap in a way that preserves the success of existing physics on smaller scales. In the standard cosmological model, which is a broad framework that describes the evolution of the universe, dark matter acts mainly through gravity and does not take part in electromagnetic interactions, while dark energy acts as a smooth component that drives accelerated expansion on the larger scales. These ingredients are not added as decoration. They are brought in because without them the observed universe would not look the way it does now. With less dark matter, galaxies would not have had enough gravitational glue to form and to stay bound for billions of years. With less dark energy, the expansion history inferred from distant supernovae and the cosmic microwave background would be different from what measurements imply. At the same time, both dark matter and dark energy remain unexplained at a fundamental level. No laboratory has yet detected a dark matter particle directly. No experiment has yet measured the energy of the vacuum of space in a way that matches the value associated with dark energy on cosmic scales. For now, these entities exist as well-tested placeholders in the equations that describe the universe, supported by a network of astronomical evidence, but not yet connected to a deeper description of matter and fields. This creates an unusual situation. Cosmology can state with reasonable confidence that most of the content of the universe is dark, and can describe in detail how that dark content shapes the overall behavior of space and structure. At the same time, the nature of this majority component remains unknown. The universe that is visible in stars and gas becomes a kind of tracer for a deeper framework that does not appear directly in any image. As measurements grow more precise and new, surveys map the sky in more detail, the inventory of the cosmos becomes more sharply defined. Ordinary matter is counted with greater accuracy. Dark matter distributions are mapped indirectly through gravitational effects, and the influence of dark energy on the expansion rate is constrained by multiple methods. The result is a model of the universe in which the dark sector is not a vague idea, but a quantitative presence with specific proportions. Yet the question of what dark matter and dark energy actually are stays open. This question becomes the central theme that guides the exploration that follows from the largest structures in the observable universe, down to the smallest proposed particles and fields, and from the earliest light to the far future shaped by forces that still hide behind gravity and expansion. For a calm observer looking at this picture, the most striking feature is its mixture of solidity and mystery. The numbers and proportions repeat across many independent measurements, giving a strong sense that the overall inventory is reliable. At the same time, the labels dark matter and dark energy act only as temporary names for behaviors that are measured but not yet understood. The universe appears both well described and deeply unfinished, and that quiet tension sets the background for every later attempt to explain how these unseen components control the fate of cosmic structures over time. On the largest scales that instruments can map, the universe does not appear as a random sprinkle of galaxies, but as a structured pattern stretching across billions of light years. Surveys that collect the light of hundreds of thousands of galaxies plot their positions in 3 dimensions, turning the sky into a volume filled with points. When these points are viewed together, they do not form a uniform fog. Instead, they line up in filaments, walls, and clusters, leaving broad regions with almost no galaxies at all. Astronomers refer to this arrangement as the cosmic web, a network of long chains and nodes of galaxies surrounding extensive voids. This pattern is not only visually striking, it also encodes how gravity expansion and the hidden dark matter have worked together over cosmic time. The starting point for this web lies in very small variations in density present in the early universe. The cosmic microwave background, the faint radiation left over from the hot beginning, shows tiny temperature differences from one patch of sky to another. These differences trace slightly denser and slightly thinner regions in the young universe, all separated by only a tiny fraction in density. As the universe expands and cools, gravity slowly amplifies these tiny imbalances. Regions that start out a little denser exert a slightly stronger pull, gather more matter and grow over time. Regions that start out thinner lose matter to their neighbours and become emptier. The result after billions of years is a network of dense filaments and nodes, separated by large voids that contain little more than a thin sprinkling of galaxies and diffuse gas. When cosmologists simulate this process in powerful computers, they often begin with a mixture of ordinary matter, dark matter, and dark energy that matches the proportions inferred from observations. The simulated universe then evolves under the influence of gravity and cosmic expansion. In these simulations, dark matter plays the main role in building the large-scale structure. Because it does not interact with light or with radiation in the same way as ordinary matter, it begins to clump earlier and more efficiently. It forms extended halos and filaments that pull ordinary matter along. Gas then falls into these dark structures, cools, and eventually forms stars and galaxies inside the pre-existing dark matter skeleton. The luminous web that telescopes see is therefore not the full structure, but a bright tracing of the underlying dark pattern. The positions of galaxy clusters, the shape of long walls of galaxies, and the measured scales of typical feature sizes can all be compared with these simulations. When the ingredients in the model are adjusted, the pattern of filaments and voids changes. The version that best matches the observed universe is one in which dark matter provides most of the mass that clusters, and dark energy provides a gentle, large-scale push that influences how quickly structures stop growing. Observations of the cosmic web come from many surveys that scan large areas of the sky and measure redshifts for galaxies. A redshift is the stretching of light to longer wavelengths as space expands during the light's journey. From the redshift astronomers infer distance, and from distance and position on the sky, they construct three-dimensional maps of galaxy locations. In these maps, filaments can stretch for hundreds of millions of light-years, while voids can span comparable distances with very few galaxies in their interiors. The clarity of this network shows that gravity has had a long time to sculpt the matter in the universe, yet also shows that structures have not grown without limit, because dark energy slows the rate at which gravity can pull new regions together on the very largest scales. One key feature of the large-scale pattern is a preferred scale related to sound waves that once moved through the hot plasma of the early universe. These waves, known as acoustic oscillations, left a faint imprint in the distribution of galaxies, a statistical tendency for pairs of galaxies to be separated by a characteristic distance. This feature acts as a kind of standard ruler across cosmic time. By measuring how this scale appears at different redshifts, cosmologists can test models of dark energy and the expansion history. The pattern of filaments and voids thus serves not only as a static picture of how matter is arranged, but also as a historical record of how rapidly space has been stretching and how strongly gravity has been able to gather matter into structure. In this picture, dark matter is not an optional detail. Without a dominant component of matter that does not interact with light, the cosmic web would look very different. Ordinary matter tightly coupled to radiation in the early universe would not have been able to form the observed structures in the available time. The presence of dark matter allows dense regions to grow earlier, setting up the scaffolding into which ordinary matter later falls. At the same time, dark energy prevents structures on the very larger scales from continuing to grow unchecked in the later stages of cosmic history, because accelerated expansion pulls distant regions apart faster than gravity can bring them together. The visible web, with its graceful filaments, massive clusters at their intersections, and wide empty voids between them, therefore encodes the combined action of dark matter and dark energy. For a careful observer, each filament and each gap is evidence that most of the work of shaping the universe has been done by components that do not appear directly in any telescope image. The maps of large-scale structure become maps of an invisible architecture, bringing into focus the idea that galaxies and clusters are only markers on a deeper, darker pattern, whose full nature is still unknown. Galaxy clusters are among the largest bound structures in the universe, gatherings of dozens to thousands of galaxies held together in a common gravitational well. Through optical telescopes, they appear as crowded fields where elliptical and spiral galaxies share the same patch of sky. Behind this simple view lies one of the earliest and most persistent clues that ordinary matter is not enough to explain how gravity works on large scales. In the early 20th century, astronomers measuring the motions of galaxies in one such cluster, The Coma cluster find that many of its member galaxies move at very high speeds relative to the cluster center. From these speeds, and from the size of the cluster, it is possible to estimate how much mass must be present to keep the system bound over billions of years. The method is straightforward in principle. If galaxies orbit inside a shared gravitational field, the typical speed of those galaxies reflects how deep the gravitational well is. High speeds require a lot of mass to keep the cluster from flying apart. When the visible content of the Coma cluster is counted, including the stars in its galaxies, and the light from any diffuse glow, the total mass that can be attributed to ordinary matter falls far short of the amount required by the orbital speeds. The difference is large, not a small correction. The observed velocities suggest that several times more mass must exist than is visible in stars. This mismatch becomes one of the first clear signs that a large fraction of the cluster's mass is dark. For some time, these early results remain uncertain. Measurements are difficult, and the nature of galaxies and clusters is still being worked out. As observational techniques improve, astronomers gain new tools to weigh galaxy clusters more accurately. One important development is the opening of X-ray astronomy. Space-based X-ray telescopes reveal that clusters are filled with very hot gas that emits brightly at high energies. This gas reaches temperatures of tens of millions of degrees and extends over distances of millions of light-years, forming a diffuse atmosphere that surrounds and fills the space between the galaxies. The total mass of this hot gas can be estimated from its brightness, and from models of how it is supported against the cluster's gravity. When added to the mass in stars, this gas increases the ordinary matter budget of the cluster by a large factor. Yet even with this additional component, the total visible mass still cannot fully account for the gravitational pull implied by the motions of the galaxies and the structure of the gas. The cluster remains too light in visible matter to hold itself together without help from something unseen. A third independent method strengthens this conclusion. According to general relativity, massive objects curve space-time and bend the paths of light. A galaxy cluster with its large mass can act as a gravitational lens, distorting and sometimes strongly magnifying the images of more distant galaxies behind it. On deep images taken with space telescopes, some clusters show elongated arcs and multiply imaged galaxies, all caused by light paths that have been bent around the cluster's mass. By analyzing the shape, position and brightness of these lensed features, astronomers can reconstruct a map of the total mass distribution in the cluster, regardless of whether that mass shines. These lensing maps consistently reveal mass concentrations that are much larger than the sum of stars and hot gas. In some cases, the peak of the mass traced by lensing does not even coincide perfectly with the brightest visible matter, suggesting that a substantial portion of the mass is a dark component that behaves differently from gas during collisions and mergers of clusters. A famous example involves a pair of galaxy clusters that pass through each other. During the collision, the hot gas from each cluster interacts, slows down and lags behind, while the galaxies, which are mostly empty space, pass by with less disturbance. Lensing studies show that the majority of the mass moves with the galaxies rather than with the slowed gas. This pattern is difficult to explain without a form of matter that does not collide and heat up like gas, but instead sails through largely unaffected, contributing gravity without emitting light. In this quiet way, cluster observations point to dark matter as a dominant component of their mass. What makes these results compelling is that three distinct techniques, each with its own uncertainties and systematic issues, tell a consistent story. Galaxy motions, hot gas structure, and gravitational lensing all require more mass than is visible, and all require that this extra mass behaves in a way that is broadly similar across many systems. Different clusters at different distances and in different environments show the same basic discrepancy. The ratio of total mass to visible mass is not exactly the same in every case, but it is always large enough that ordinary matter alone cannot explain the observations. Clusters that ought to disperse over cosmic time according to visible matter alone remain stable and bound because a dominant dark mass component holds them together. In modern cosmology, these results become part of a broader effort to measure how much dark matter the universe contains. Surveys count clusters at various epochs, measure their total masses, and compare the abundance of massive clusters to predictions from models in which structure grows from small initial fluctuations. The number of very massive clusters at different times is sensitive to how much matter, especially dark matter, is available to collapse under gravity, and to how dark energy affects the growth of structure by altering the expansion rate. By matching the observed cluster population to theoretical predictions, cosmologists can infer both the fraction of the universe made of dark matter and the strength of dark energy's influence on structure formation. These studies reinforce the view that dark matter provides most of the gravitating mass that builds and stabilizes clusters. At the same time, they underline how little is known about its microscopic nature. In many models, dark matter consists of particles that interact very weakly with ordinary matter and with themselves apart from gravity. If that picture is correct, then clusters are enormous laboratories in which the bulk behavior of these particles is written on the sky as arcs, hot gas atmospheres, and stable groupings of galaxies that defy simpler expectations. If alternative ideas about gravity are considered in which the law of gravity changes on large scales, then clusters become strict tests of those modifications, because any change must reproduce the detailed cluster observations, while also matching the behavior of galaxies and the large-scale structure. In either case, the data from clusters leave no easy escape from the conclusion that something beyond ordinary luminous matter shapes their dynamics. In the calm light of these systems, the mystery of the dark sector takes on a concrete form. Here are structures that can be seen weighed and followed through time, yet their stability and history depend on a component that is inferred only through its gravitational pull. Galaxy clusters, far from being mere background scenery in the cosmos, stand as clear signposts that the universe is built upon foundations that remain hidden, and that whatever dark matter may be, it has already guided the largest bound systems in the universe for billions of years. Individual galaxies provide another very direct way to see the action of dark matter. A spiral galaxy, when studied in detail, is not only a flat image of arms and a bright center, it is a rotating system in which stars, gas and dust orbit around a common center under the pull of gravity. By measuring how fast different parts of a galaxy move as a function of distance from the center, astronomers can construct what is called a rotation curve. This curve shows orbital speed on one axis and radius on the other. For systems governed mainly by a central concentration of mass, such as a planetary system dominated by a single star, the expected trend is that orbital speeds rise near the center and then gradually fall with increasing distance because the gravitational pull becomes weaker far from the main mass. When astronomers first begin to measure rotation curves of spiral galaxies with radio telescopes and optical spectroscopy, they expect to see a similar pattern. Instead, the data show something different and persistent. Beyond the bright central regions where most of the visible stars are located, the orbital speeds of gas and stars do not fall as expected. They level off and remain almost constant out to large radii far beyond the main disk of luminous matter. In some galaxies, the rotation curve even rises slightly at large distances. This flat or slowly rising behavior indicates that the total enclosed mass continues to grow with radius even where the visible matter thins out. The gravitational field is stronger than it should be if only the observed stars and gas were present. The simplest way to explain this is to suppose that each galaxy is surrounded by an extended halo of unseen mass that adds to the gravitational pull at large distances. In the standard dark matter picture, these halos are made of dark matter that does not emit or absorb light, but that responds to and produces gravity in the usual way. In this view, the bright disk of a spiral galaxy sits embedded in a larger, nearly spherical or mildly flattened distribution of dark matter that extends well beyond the visible edge. Rotation curves of many galaxies, from large luminous spirals to small dwarf systems, support this general picture. The shape of the curve and the degree of flatness may vary, but the recurring theme is that more mass is required than can be accounted for by stars and gas alone. Careful modelling of individual galaxies uses the observed light distribution to estimate the contribution of stars, the measured gas content to estimate its gravitational effect, and then attributes the remaining required mass to a dark halo. When many galaxies are studied in this way, a pattern emerges. There is a relationship between the total mass of dark matter in the halo and properties of the visible galaxy, such as its luminosity and the characteristic speed at which its outer parts rotate. This link hints at a close connection between how galaxies form and the dark environments in which they live. The explanation that dark matter halos surround galaxies is not the only possible way to interpret flat rotation curves, but it is the one that fits smoothly with other lines of evidence. Alternatives that modify the law of gravity on low acceleration scales can reproduce some rotation curves without invoking large amounts of unseen matter, at least in simplified systems. However, when galaxy rotation data are combined with the cluster evidence, the cosmic web and the cosmic microwave background, the dark matter framework offers a consistent description across many different scales and epochs. In that framework, individual galaxies are one more laboratory where the same unseen component acts in a predictable manner. From this perspective, the rotation curves are not isolated puzzles, but detailed maps of how dark matter mass is distributed inside halos. Observations at radio wavelengths are especially important in building this picture. Cold hydrogen gas in galaxies emits radiation at a characteristic wavelength that can be measured even when the gas is too faint to be seen in starlight. This emission traces gas out to large radii and provides a way to extend rotation curves well beyond the bright optical disk. These extended measurements show that the flat behavior often continues far into the outer regions, supporting the idea that the dark halo is much larger than the luminous part of the galaxy. In some nearby systems, the rotation curve can be followed to distances several times the visible radius, and still the speeds remain high. The mass implied by this motion is several times larger than the mass of visible matter. Dwarf galaxies provide another important test. They are small systems with relatively few stars and low total luminosities. In such galaxies, ordinary matter makes up a small fraction of the total mass, and the gravitational influence of dark matter can be especially strong. Rotation curves or internal velocity measurements of dwarf galaxies often indicate that they are dominated by dark matter at nearly all radii. This suggests that the dark component is not just an outer addition to large spirals, but a central ingredient in even the smallest galactic systems. It shapes not only the overall structure, but also the internal dynamics of galaxies across a wide range of sizes. The picture becomes richer when gravitational lensing is added. Some galaxies act as lenses for even more distant background sources, bending their light and creating multiple images or distorted shapes. Lensing mass estimates for lens galaxies can be compared with the mass inferred from rotation and from the visible content. These comparisons again point to significant amounts of dark matter arranged in halos, whose properties are broadly consistent with those required by rotation curve modelling. In this way, two independent probes, motion and lensing, converge on the same conclusion. For cosmology, rotation curves do more than reveal the presence of dark matter. They also constrain what kind of dark matter is possible. The inner shape of the halo, how sharply or smoothly its density rises toward the centre, and how the halo mass relates to the visible disk place limits on models in which dark matter particles move very fast or interact in special ways. If dark matter were too hot, meaning that its particles had very high speeds in the early universe, it would erase small-scale structures and lead to very different galaxy rotation properties from those that are observed. The fact that galaxies of many types share broadly similar halo features supports models in which dark matter is cold, or at most mildly warm, with particles that move slowly enough to allow fine-scale structure to form. At the same time, small differences between observed rotation curves and simple models motivate further study of both dark matter physics and the complex behavior of ordinary matter in galaxies. In the calm summary that emerges from this work, individual galaxies are no longer just collections of stars arranged in various shapes. They are systems in which the visible parts are supported and controlled by a much larger invisible component. The steady speed of gas and stars far from the centre is a clear sign that the gravitational field remains strong where light grows faint. Each flat rotation curve is therefore a detailed quantitative statement that dark matter contributes most of the mass of the galaxy. Together with cluster studies and large-scale mapping, these galactic measurements tie the idea of dark matter to direct repeatable observations. They show that the unseen mass is not an abstract adjustment in equations, but a structured, organized presence that shapes the everyday dynamics of galaxies throughout the universe. Dark matter halos are not only accounting devices that explain extra gravity in galaxies, they are also central actors in the story of how galaxies form, grow, and change over cosmic time. In the early universe, soon after the first light appears, small fluctuations in the density of dark matter begin to collapse under their own gravity. Because dark matter does not interact strongly with radiation, it can start to clump earlier than ordinary matter. These initial clumps merge and grow into larger halos, producing a nested hierarchy of dark structures. Ordinary gas, which is coupled to radiation in the hot early universe, falls into these halos once it can cool and decouple efficiently. In this way, the dark matter distribution sets the places where the first galaxies can appear, because it provides deep gravitational wells that gather the gas needed to form stars. As time goes on, halos continue to merge. Smaller halos fall into larger ones, and galaxies that have already formed inside them are carried along. When halos merge, their galaxies may collide, disturb each other, and sometimes eventually coalesce. The result is that the formation of galaxies is guided at every stage by the assembly history of their dark halos. A massive halo that forms early and grows through many mergers is likely to host a large galaxy, possibly with an extended stellar halo and a surrounding population of satellite galaxies. A less massive halo, or one that assembles its mass later and more quietly, may host a smaller, more fragile system. In this way, the mass and growth pattern of the dark halo influence the size, shape, and stellar content of the visible galaxy. Computer simulations that include dark matter and gas make this connection clear. In these models, dark matter particles trace out a complex network of halos that grow and merge over billions of years. Gas falls into these halos, settles into rotating disks, and forms stars where it becomes dense enough. Feedback from stars and from central black holes can heat or expel gas, changing how efficiently the galaxy turns its gas into new stars. Yet throughout these processes, the underlying dark halo remains the main container that sets the overall gravitational field. It determines how fast material can fall, in how stable the galactic disk can be, and how easily the system can retain or lose gas after energetic events. By comparing the statistical properties of simulated galaxies with observations, astronomers infer that there is a fairly regular relation between halo mass and the total mass in stars. This relation is not perfect, but it suggests that halos of intermediate mass are most efficient at forming stars, while very small and very large halos convert only a small fraction of their gas into long-lived stars. the shape of the halo also matters. In the simplest models, dark matter halos are roughly spherical and smooth with densities that rise toward the center and fall off with radius. More detailed calculations show that halos can be slightly elongated and can contain many subhalos, smaller clumps of dark matter that survive as the larger halo grows. These subhalos can host satellite galaxies such as small dwarf systems orbiting a larger host. In the case of the Milky Way, a number of dwarf galaxies orbit within the extended dark halo, each one likely embedded in its own subhalo. Their motions and spatial distribution offer clues to the structure of the larger halo and to the properties of dark matter itself. If dark matter interacts with itself, or has a particular range of particle velocities, the number and concentration of subhalos would be affected. Observations of satellite populations therefore provide indirect tests of dark matter models using the arrangement of galaxies in and around halos. Halos also influence the internal structure of the galaxies they host. For spiral galaxies with thin extended disks, the depth and shape of the halo potential help set the rotation speed of the disk and its stability against disturbances. A deeper halo can protect a disk from being easily disrupted in minor mergers, while a shallower halo may allow interactions to thicken or transform the disk more readily. For elliptical galaxies, which often form through major mergers of disk systems, the surrounding halo mass and its merger history shape the final stellar distribution and the motions of stars. Even the central regions where supermassive black holes grow are affected by how gas is delivered through the halo over time. In this sense, halos are regulators that do not appear directly in visible light, yet set many of the conditions under which galactic structures can arise. Beyond individual systems, halos connect galaxies to the larger environment. Along filaments of the cosmic web, halos accrete material and sometimes align their spins with the larger scale flows of matter. Groups and clusters of galaxies can be seen as halos, surrounded by halos, with a main dark matter structure that contains many smaller ones. The infall of halos along filaments feeds clusters over time, bringing in galaxies whose gas and stars then feel the new, deeper, gravitational field. In regions where dark matter density is high, galaxy formation proceeds differently from regions in large voids where halos are rarer and less massive. Thus, the variation in halo mass and environment across the universe contributes to the diversity of galaxies that are observed. In the present universe, dark matter halos record the history of structure formation. They preserve information about when and how a galaxy's mass was assembled, even when the visible components have been stirred and reshaped by interactions. Stellar disks can be warped, bars can form and dissolve, and gas can be accreted or expelled, yet the extended halo continues to define the deep gravitational context. Observers probe this context by measuring rotation curves, satellite motions, and gravitational lensing, building up an increasingly detailed picture of where the mass resides. Each new survey that refines halo maps also tightens the constraints on any possible model of dark matter. Through this layered view, galaxies are understood as bright, complex systems living inside even larger and longer-lived dark structures. The visible parts trace only a fraction of the full mass, but they respond sensitively to its distribution. Dark matter halos shape where galaxies appear, how they grow, and how they interact with their neighbours. They provide the quiet, invisible framework within which the luminous universe takes form, even as their own composition remains one of the most important open questions in modern cosmology. Gravitational lensing offers a way to see mass without relying on light, and in doing so it provides some of the clearest maps of dark matter in the universe. According to general relativity, mass and energy curve spacetime and light follows the curved paths that result. When a massive object such as a galaxy or a galaxy cluster lies between an observer and a more distant source, the foreground mass can bend the light from the background object. The distant source may then appear distorted, magnified, or split into multiple images. This effect is called gravitational lensing, and it turns galaxies and clusters into natural lenses that reveal how mass, including dark matter, is distributed along the line of sight. In strong lensing cases, the alignment between the lens and the background source is close enough, and the mass of the lens large enough that the distortion becomes dramatic. A single background galaxy can appear as several separate images, as thin arcs wrapped around the lens, or even as a nearly complete ring when the alignment is very precise. The geometry of these images depends on the position and distance of the source, the geometry of the universe, and the detailed mass distribution in the lens. By modelling the lens system, astronomers can reconstruct a map of the total mass, including both visible and dark components. Often these maps reveal mass peaks that are smoother or more extended than the light distribution alone would suggest. In some systems, the centre of mass inferred from lensing does not coincide exactly with the brightest galaxies or the densest gas. These small offsets and the overall shape of the mass map indicate that dark matter contributes significantly to the lensing signal and can be distributed differently from ordinary matter, especially after past interactions and mergers. Beyond these striking strong lens examples, there is also weak lensing, where the distortions of individual background galaxies are very small. A single image may show only a subtle stretch, or shear, that is impossible to interpret by eye. However, when many thousands or millions of background galaxies are imaged over large areas of sky, their shapes can be combined statistically. Tiny preferred alignments in their apparent orientations reveal an average shear pattern imprinted by the foreground mass. By analysing these patterns, astronomers can construct a projected map of mass known as a mass density field. This method does not require the mass to emit light, so it is sensitive to dark matter as well as to ordinary matter. Large weak lensing surveys using ground-based telescopes and space observatories have created wide maps where the peaks in the mass distribution often correspond to known clusters and groups of galaxies, while many smaller fluctuations trace filaments and less obvious structures. In these maps, dark matter appears as a web-like network very similar to that seen in simulations. Ordinary matter marks only part of this network. The lensing reconstructions show that the underlying dark mass often extends beyond the visible outlines of galaxies and clusters, sometimes bridging regions where little light is seen. Gravitational lensing is especially powerful because it responds directly to the gravitational field integrated along the path of light. It is not sensitive to how matter is partitioned between stars' gas and dark matter. It only cares about the total. This allows lensing to cross-check mass estimates derived from other methods. For example, the mass of a galaxy cluster inferred from galaxy motions and X-ray emitting gas can be compared with the lensing mass. In many cases, the agreement is good within uncertainties, reinforcing the idea that dark matter dominates the total mass budget. In some systems, discrepancy can appear and may point to complex geometries, projection effects, or unusual dynamical states such as recent mergers. These differences, when understood, can refine models of how dark matter and ordinary matter behave in dynamic environments. Lensing also offers clues about how collisional or collisionless dark matter might be. During cluster mergers, the hot gas components can slow down and pile up due to collisions, while galaxies and any non-collisional dark matter continue more freely. By mapping where the lensing mass peaks lie relative to the gas and the galaxies, astronomers can test whether dark matter appears to feel drag forces or whether it moves almost unimpeded. Observations to date generally favour a picture in which dark matter interacts little with itself or with ordinary matter, apart from gravity, at least on these scales. This does not uniquely determine the particle nature of dark matter, but it rules out some models in which dark matter would collide strongly and produce very different mass and light separations during mergers. On even larger scales, weak lensing becomes a tool for studying the growth of structure over cosmic time, which is influenced by both dark matter and dark energy. As the universe expands, gravitational instability allows regions with slightly higher density to grow as matter flows in. The rate at which structures grow depends on how much dark matter there is, and on how strongly dark energy accelerates expansion. If dark energy is very strong, it can slow the growth of new structures by stretching space so rapidly that distant regions move beyond each other's gravitational reach. By measuring the lensing signal for galaxies at different distances, astronomers can build a form of lensing tomography, slicing the universe into redshift layers and tracing how the mass distribution evolves. The results are compared with cosmological models to check whether the observed growth of structure matches predictions for a given mixture of dark matter and dark energy. In many current analyses, the broad agreement is good, but some tensions and small differences have appeared between lensing-based measurements and other probes. These may be due to unrecognized systematic effects in the data or modeling, or they may hint at late-time changes in the behavior of dark energy, or in the law of gravity on large scales. At present, the community treats these tensions, cautiously improving surveys and analysis methods to see whether they persist. Regardless of the outcome, gravitational lensing remains one of the cleanest ways to tie together the mass distribution and the geometry of the universe. It does not require assumptions about the state of the gas or the motions of galaxies. It simply follows the bending of light. For dark matter studies, lensing has turned abstract curves and densities into detailed maps in which the dark component appears as a structured, quantifiable presence. For dark energy, lensing monitors how structure grows under the competing influences of gravity and accelerated expansion. Together with other observations, these lensing results reinforce the picture of a universe where the dark sector sets the stage, while the luminous matter provides only the most visible but not the dominant part of the cosmic landscape. For a quiet scientific narrative, gravitational lensing stands as a calm yet powerful line of evidence. It shows that even when light cannot reveal everything directly, its path through the universe carry the imprint of mass and energy. Reading that imprint has allowed cosmology to move from rough estimates of missing mass to detailed image-based reconstructions of the dark matter web, all while leaving open the deeper question of what at the fundamental level this invisible mass is made of, and how exactly dark energy shapes the backdrop through which every beam of light travels. The region of space that holds the Milky Way, the Andromeda Galaxy, and a collection of smaller galaxies is known as the local group, and it offers a closer view of how dark matter shapes environments on intermediate scales. On the sky, these galaxies appear as separate islands of stars, each with its own structure and internal dynamics. In three-dimensional space, they are bound together in a modest collection, a few million light-years across itself, part of a larger association of groups and clusters embedded in the cosmic web. The motions of galaxies within the local group, the distribution of satellite systems and the presence of diffuse gas all point to an underlying dark framework that ties the region together. The Milky Way and Andromeda are the two dominant galaxies in this group. Each is surrounded by an extended dark matter halo that reaches far beyond its visible disk and stellar halo. These halos overlap in the space between the galaxies, and their mutual gravity governs the future of the local group. Measurements of the motion of Andromeda relative to the Milky Way show that the two galaxies are moving toward each other, not apart. In a universe whose large-scale expansion is accelerating, it may seem at first that all galaxies should recede from each other. On smaller scales, however, local gravity can overcome the general expansion. The dark matter halos of the Milky Way and Andromeda create a shared gravitational well in which both galaxies move along with their satellites. Over billions of years, this attraction is expected to bring the two main galaxies together in a merger that will transform their shapes and mix their star's gas and dark matter. The timing and details of this future encounter depend on the mass and structure of the halos, which are inferred from a combination of stellar motions, satellite dynamics, and models of the overall local group. In the present era, the local group contains not only these two large spirals, but also dozens of dwarf galaxies. Many of these satellites orbit within a few 100,000 light-years of their hosts, and their motions provide important clues about the depth and shape of the surrounding dark matter halos. Dwarf galaxies in the local group often show internal velocity dispersions that can only be explained if they are themselves embedded in dark matter subhalos. Their stars move too fast within the small visible extent to be held together by starlight alone. This suggests that dark matter is present not just as a smooth extended halo, but also as a collection of smaller clumps that host their own miniature galaxies. Comparing the observed number and distribution of these satellites with predictions from dark matter simulations has become a precise test of dark matter models. Early simulations of cold dark matter predicted more subhalos than the observed number of dwarf galaxies, leading to a puzzle sometimes called the missing satellites problem. Over time, better simulations that include the effects of gas physics, star formation, and feedback processes have shown that many low-mass halos may remain dark, forming few or no stars, while only some become visible dwarf galaxies. This reduces the tension and illustrates how the interplay between dark matter and ordinary matter can shape what is seen. The local group also participates in the motion of larger structures. Beyond the immediate neighborhood, many groups and clusters, including the local group, appear to move relative to the average rest frame of the cosmic microwave background. These bulk flows are thought to arise from the gravitational attraction of large-scale overdensities in the surrounding matter distribution, including both dark and ordinary components. In this picture, the local group is not isolated but falls along the potential wells defined by dark matter, on scales of tens to hundreds of millions of light-years. Surveys that measure distances and velocities for many galaxies in the region around the local group help map these flows and identify possible attractors such as dense superclusters. These studies reinforce the idea that dark matter provides the main contribution to the gravitational field on these scales, guiding the motion of groups and clusters in a way that is consistent with the observed large-scale structure. Within the Milky Way itself, efforts to map the dark halo use a variety of tracers. The motions of stars in the outer halo, the orbits of globular clusters, streams of stars that were once part of disrupted dwarf galaxies, and the pattern of gas rotation all contribute to estimates of how mass is distributed beyond the visible disk. In some cases, long thin stellar streams wrap around the galaxy, tracing out past orbits of satellite systems that have been tidally stripped. The shape and precession of these streams are sensitive to the form of the dark halo, offering a way to test whether it is more spherical, flattened, or triaxial. Early results suggest that the halo is extended and roughly comparable in scale to that inferred from galaxy formation models, although details remain under active study. Andromeda observed from outside provides a complementary case where its own satellites and halo structure can be mapped in a different geometric configuration. Together, the Milky Way and Andromeda form a kind of natural laboratory pair, offering two examples of massive halos in a common environment. The local group environment also shapes how dark energy appears in practice. On the scales of the group, dark energy does not break apart the bound structure. Its effect is small compared to the local gravitational pull of the combined halos. However, on the boundaries of the group where the gravitational binding becomes weaker, dark energy contributes to the overall expansion that carries more distant galaxies away. Between the local group and nearby groups, space continues to expand, and this expansion gradually separates bound systems from each other. In this way, the local group exists as a gravitational island within a wider sea of expanding space whose behavior is influenced by dark energy. Over very long timescales, this contrast is expected to sharpen. Bound structures remain together while the distances between them grow ever larger. For now, the local group sits at an intermediate scale where both dark matter and dark energy play roles that can be teased out through careful measurements. Dark matter dominates the internal mass budget and controls the motions of member galaxies, while dark energy influences the background against which the group moves and the long-term destiny of its connections to other structures. In a calm summary, the local group shows how the dark sector shapes a familiar environment. The Milky Way, the galaxy that holds the Sun, is not an isolated bright disk in an empty void. It is one part of a multi-galaxy system held together by a shared dark halo itself drawn along paths set by larger dark structures. Every satellite galaxy, every extended stream of stars, and every measured bulk flow provides another data point that links the everyday scale of galactic astronomy to the deeper framework of dark matter and dark energy. In this nearby setting, the abstract concepts of halos, subhalos, and cosmic expansion become concrete patterns in motion, revealing that even close to home, the universe is guided by components that remain unseen, yet clearly present in their gravitational effect. Closer to the Sun, dark matter becomes less a grand scaffold for galaxies and more a quiet background component that slips unnoticed through planetary orbits, spacecraft trajectories, and the interstellar medium. The solar system moves through the Milky Way on an orbit that takes hundreds of millions of years to complete circling within the galactic disk and dipping slightly above and below its midplane. In addition to the known gravity of the stars, gas and dust in this region, there is an extra mass density that is inferred from the overall rotation of the galaxy and from models of the Milky Way halo. This extra density is attributed to dark matter, and it implies that in the solar neighbourhood, an invisible population of particles is continually passing through the space occupied by the planets. On scales of planetary orbits, the gravitational effect of this local dark matter is very small compared to the pull of the Sun, so spacecraft navigation and planetary motion can be described accurately without including it. However, on slightly larger scales, such as the thickness and stability of the galactic disk, the presence of dark matter becomes important. The Sun and its neighbours move inside a combined gravitational field created by both visible matter and the local part of the dark halo. This field shapes the vertical oscillations of stars above and below the disk and contributes to the overall pattern of motions seen in surveys of nearby stars. By measuring these motions, astronomers can estimate the total mass density in the neighbourhood, and by subtracting the contribution from visible matter, they infer the local dark matter density. This provides key input for efforts to detect dark matter particles directly on Earth. If dark matter is made of particles, then as the solar system moves through the galactic halo, these particles should continually stream through any detector placed underground or in space. Their individual masses and interaction strengths are unknown, so experiments must search over a wide range of possibilities. Many direct detection experiments use large volumes of very pure materials, such as liquid xenon, germanium crystals, or other carefully chosen targets shielded from cosmic rays and background radiation by thick layers of rock or water. The idea is that once in a while a dark matter particle might collide with a nucleus in the detector, imparting a small amount of energy that can be measured as a flash of light, a tiny rise in temperature, or an ionization signal. The expected interaction rate depends on the local dark matter density and on the detailed properties of the hypothetical particle. Over the past decade, successive generations of experiments have probed smaller and smaller interaction strengths and wider ranges of mass. Each new detector improves sensitivity by increasing the target mass-reducing backgrounds and refining the analysis. So far, no unambiguous signal has been confirmed. A few experiments have reported hints of excess events that might be compatible with dark matter, but follow-up studies and competing experiments often fail to see the same pattern. As a result, the parameter space of some popular candidate particles, such as weakly interacting massive particles, has been progressively narrowed. The absence of detection in this range is not a failure, but a strong constraint. It rules out large regions of mass and interaction strength that once seemed plausible, pushing theorists to consider new models and different classes of particles such as lighter, dark matter, or candidates that interact through different channels. Another class of searches focuses on axion-like particles, very light hypothetical particles that could also make up dark matter. These experiments use resonant cavities, strong magnetic fields, or other devices to look for small conversions between axions and photons. Here too, no confirmed detection has appeared, but sensitivity continues to improve scanning through different possible masses and couplings. In addition to direct detection, there are indirect searches that look for products of possible dark matter annihilation or decay, such as gamma-rays, neutrinos, or charged particles coming from regions where dark matter density is high. These could include the center of the galaxy dwarf spheroidal galaxies, or even the Sun if dark matter can be captured inside it. Some observations have reported intriguing excesses in certain energy ranges, but none has yet led to a widely accepted identification of dark matter. Background processes in astrophysical sources can often mimic or explain the signals. In this way, indirect searches provide potential clues and constraints, but have not yet delivered a definitive answer. The environment near the Sun is also used to test how much dark matter can exist without contradicting well-measured phenomena. The precision of planetary ephemerides, the tracking of spacecraft, and the careful monitoring of binary pulsars place limits on any additional gravitational pull that could come from a dense dark matter component localized within the solar system. These studies show that any extra mass concentrated close to the planets must be small compared with the mass of the Sun and planets themselves. This is consistent with the broader picture of dark matter as a smoothly distributed halo on galactic scales, rather than as dense clumps inside planetary systems. The local dark matter density inferred from galactic models is enough to inform direct detection experiments, but not enough to change the basic architecture of the solar system. Large surveys of stars in the Milky Way disk complement these local tests. By mapping the velocities and positions of millions of stars, they construct a detailed view of the gravitational potential in which those stars move. Subtle features in these motions can reveal ripples or waves in the disk that might be caused by past encounters with satellite galaxies, or by the overall structure of the dark halo. These effects provide another way to probe the local distribution of dark matter, although they must be disentangled from the rich internal dynamics of the disk itself. In this layered picture, the solar neighborhood becomes a meeting point between particle physics and galactic dynamics. On the one hand, the local density and velocity distribution of dark matter particles set by the Milky Way halo define the conditions under which detectors on Earth operate. On the other hand, the results of those detectors feed back into cosmological models by constraining what the dark matter can be. If a particular particle candidate is ruled out, models that rely on that candidate must be revised. If a signal is ever confirmed, its properties would connect directly to the larger scale behavior of halos and the formation of structure throughout the universe. For now, the situation is one of informed waiting and gradual refinement. The presence of dark matter in the solar neighborhood is strongly supported by galactic studies, yet its particle nature remains hidden. Experiments sink deeper underground, become quieter and more sensitive, and expand their reach in mass and interaction strength, while astronomical surveys sharpen the estimates of local density and velocity patterns. Together they narrow the range of possibilities, but many viable models remain. The Sun continues its slow orbit through the Milky Way, carrying Earth and its instruments through a sea of unseen particles that, if the dark matter picture is correct, are present at all times. Their gravitational influence on the local environment is steady and modest, but their existence would link this quiet corner of the galaxy to the grander dark framework that supports every structure in the universe. Until a direct detection is made, dark matter near the Sun remains a carefully inferred presence, its properties bounded by an expanding web of constraints, yet still open enough to sustain multiple hypotheses. In this calm but unresolved state, the solar neighborhood stands as a reminder that even in regions that feel well known, the majority of matter may still belong to a sector that has not yet revealed its basic ingredients. The expanding universe reveals another side of the dark sector, one that relates not just to how matter is arranged, but to how space itself behaves over time. In the early 20th century, astronomers and physicists begin to consider solutions of general relativity, in which the universe is not static but dynamic, either expanding or contracting. At first, many still assume that the cosmos on the larger scales is unchanging in time, a quiet backdrop for galaxies that move only within it. This assumption starts to shift when observations of distant galaxies show a systematic trend in their light. Spectra taken with large telescopes reveal that characteristic lines of elements in those galaxies are shifted toward longer wavelengths compared with the same lines measured in laboratories on Earth. This shift toward the red end of the spectrum, known as redshift, can arise when a source moves away, stretching the light, or when space itself expands while the light is in transit. In 1929, measurements of many galaxies at different distances show that on average more distant galaxies display larger redshifts. This relation suggests that the universe is expanding with space stretching between galaxies over time so that the wavelengths of the light grow longer during their journey. From this point onward, the idea of a static universe gradually gives way to a picture in which the cosmos has a history, with earlier epochs denser and hotter than the present. In the expanding universe, picture galaxies are often described as receding from one another, but on large scales it is more accurate to say that the fabric of space between them is stretching. Individual galaxies, especially those that are bound within groups and clusters, do not drift apart internally. Their own gravity keeps their stars together. Instead, the distances between far separated groups of galaxies increase as the scale of the universe grows. Light emitted long ago, when everything was closer together, carries a record of how much expansion has occurred since its emission. By measuring redshifts and estimating the distances to galaxies, astronomers can reconstruct a rough expansion history. For many decades, this history is expected to follow a simple pattern. The expansion might begin rapidly after a hot early phase, and then gradually slow as gravity from all the matter in the universe pulls back on the motion. Depending on how much total matter there is, the expansion could slow but never stop, or it could halt and reverse, leading to a future contraction. In any case, the intuitive expectation is that gravity should resist expansion, not enhance it. The task is to measure how strong that resistance is, and to infer the total amount of matter, both visible and dark, from the way the expansion decelerates. To carry out this program, astronomers need reliable distance indicators for faraway galaxies. One class of objects that serves this purpose is Type 1, supernovae stellar explosions that reach very high and fairly uniform peak luminosities. Because they are bright, they can be seen across large fractions of the observable universe. Careful observations and calibrations show that their light curves can be standardized, so that the observed brightness provides an estimate of distance. When combined with redshift measurements, these distances allow a mapping of how the expansion rate has changed over time. In the late 20th century, teams that gathered data on many distant Type 1, a supernova, make a surprising discovery. Instead of finding that the expansion is slowing, in a way consistent with a universe dominated by matter, they find that distant supernovae are dimmer than expected. This suggests that these supernovae are farther away than they would be in a simply decelerating universe. The implication is that the expansion has been speeding up, not slowing down over the recent billions of years. This result is checked and rechecked compared with other measurements and analysed with independent methods. The conclusion that the universe is undergoing accelerated expansion holds up under scrutiny. To explain this acceleration within general relativity, cosmologists introduce a component with negative effective pressure that acts as a kind of repulsive gravity on large scales. This component is called dark energy. One simple way to describe dark energy is as an energy density associated with empty space itself, sometimes linked to the cosmological constant term in Einstein's equations. If the vacuum of space carries a small, nearly constant energy density, then as the universe expands and more space comes into existence, the total dark energy content grows, maintaining a constant density. This energy influences the expansion by pushing space to expand faster. In a universe with both matter and dark energy, the early expansion is dominated by matter, so structures can form as gravity pulls material into growing over densities. Later, as the average matter density drops with expansion, while the dark energy density stays nearly constant, dark energy becomes dominant and begins to accelerate the expansion. The discovery of accelerated expansion shifts the focus of cosmology from simply measuring how much matter exists to also determining the properties of dark energy. The relative amounts of ordinary matter, dark matter and dark energy affect the detailed expansion history, which can be probed by combining supernova data with other observations such as the cosmic microwave background and the large-scale distribution of galaxies. Together, these measurements point to a universe in which dark energy supplies about 70% of the total energy content with dark matter, providing most of the rest and ordinary matter a small remainder. This composition explains why expansion is accelerating now, and why structures could still form in the past. At the same time, the physical nature of dark energy remains unknown. It might behave exactly like a cosmological constant unchanging over time and space, or it might vary slowly as in models where a scalar field rolls in a potential. In either case, dark energy is not something that can be seen or isolated in a laboratory. Its presence is inferred entirely from its effect on the expansion and on the growth of cosmic structure. On human timescales, the acceleration is extremely gentle. The change in the expansion rate over a single lifetime is far too small to notice directly. Yet over billions of years, the influence of dark energy reshapes the large-scale structure of the universe. Regions that are not bound by their own gravity are carried away from each other ever more quickly. The formation of new massive clusters slows and eventually nearly stops, because matter at large separations can no longer collapse together when space between it is expanding so rapidly. The cosmic web becomes effectively frozen on very large scales, while internal evolution continues more quietly within already bound systems. From the point of view of the underlying equations, dark energy adds a relatively simple term. From the point of view of fundamental physics, however, it raises difficult questions. Quantum field theories that describe particles and their interactions predict contributions to the vacuum energy that are far larger than the tiny value implied by cosmic acceleration. Reconciling these estimates with observations is a major open problem. It suggests that some cancellation or new principle must be at work, but no agreed explanation yet exists. Thus, the expanding universe serves as a stage on which the influence of dark energy becomes visible. Redshift measurements, supernova-like curves, and detailed surveys of large-scale structure together show that space is not only stretching, but doing so at an increasing rate. This behavior cannot be explained by matter alone even when dark matter is included. A new component is needed, one that does not clump like matter, but exerts a smooth, persistent influence on the overall geometry of space-time. That component called dark energy now appears as the dominant driver of the universe's long-term evolution. The precise form it takes, whether as a cosmological constant, a slowly changing field, or something not yet imagined, remains uncertain. However, its effect on the expansion is written clearly in the light from distant galaxies and exploding stars. In this calm, observationally anchored picture, dark energy is not a speculative add-on, but a necessary part of any model that aims to describe the universe from its early hot phases to its present accelerating state. At the same time, the gap between the simplicity of its effect and the difficulty of explaining its origin stands as one of the most enduring mysteries in modern cosmology, hinting that the story of how space expands may still be missing a crucial piece. Type 1. Supernovae play a central role in how cosmology infers the presence and strength of dark energy. These stellar explosions arise in binary systems, where a white dwarf, the compact remnant of a once normal star, gains matter from a companion until conditions allow a thermonuclear runaway to occur. The precise details of this process are still topics of active research, but one robust outcome is that Type 1 supernovae reach a characteristic peak luminosity that is similar from event to event. This makes them useful as standardizable candles. By comparing their known intrinsic brightness as calibrated from systems in the nearby universe with their observed brightness at larger distances, astronomers can estimate how far away they are. When these distances are plotted against redshifts, the resulting relation traces the expansion history of the universe. For much of the 20th century, the goal of such measurements is to determine how quickly the expansion is slowing under the influence of gravity from matter. When dedicated supernova search programs begin to discover and monitor large numbers of distant Type 1 explosions, they provide the data needed to extend the distance, redshift relation to earlier cosmic times. Teams use wide-field telescopes to scan patches of sky, identify new points of light that slowly brighten and fade, and then follow up with more detailed observations. The shape of the light curve, how the brightness rises and falls over weeks, carries information that allows the intrinsic luminosity to be standardized, more precisely reducing scatter in the distance estimates. When the first large samples of distant Type 1 supernovae are analyzed in this way, the resulting Hubble diagram does not match expectations for a universe in which matter alone governs the expansion. The supernovae at high redshift appear fainter than they would in a simply decelerating model, implying that they are farther away. This can be understood if the expansion has been speeding up over the time the light has been travelling. In such a scenario, galaxies at a given redshift are more distant than they would be if the expansion had been slowing consistently. The degree of faintness combined with the overall shape of the distance redshift curve points to an accelerating universe with a positive dark energy density. Importantly, this conclusion emerges from two independent collaborations using different telescopes analysis methods and sets of supernovae. This parallel effort provides a strong check against simple observational bias. Even so, the stakes are high, and careful work goes into checking for possible systematic effects. Intervening dust, for example, can dim light, and could in principle make distant supernovae appear farther away than they are. However, dust usually reddens light as well as dimming it, and the observed colours of the supernovae can be modelled to estimate and correct for dust extinction. Different populations of supernovae and different kinds of host galaxies might also have slightly different intrinsic brightnesses. Surveys therefore study correlations between supernova properties and their environments, adjusting calibrations to account for such trends. Over the years, improved data beta calibrations of nearby Type 1 a supernova and cross-checks with other distance indicators have strengthened the original conclusion rather than weakening it. The acceleration signal persists when more supernovae are added, including events at both lower and higher redshifts. As the supernova datasets grow, they begin to constrain not only the presence of dark energy, but also its properties. In many models, dark energy is described by an equation of state parameter that relates its pressure to its energy density. A pure cosmological constant has a specific fixed value of this parameter. By fitting models with different values to the distance, redshift relation cosmologists can test whether the data are consistent with a constant dark energy density or favour a slowly evolving one. Current analyses combining supernova with other cosmological probes generally find that the simplest constant dark energy model fits the data well within present uncertainties. However, small deviations cannot yet be ruled out. Future surveys aim to improve the precision of these measurements, extending the reach to higher redshifts and increasing the number of well-observed supernovae in order to detect any time variation in the dark energy component if it exists. Supernova observations do not stand alone. They are part of a network of measurements that includes the cosmic microwave background, baryon acoustic oscillations in the galaxy distribution, and weak gravitational lensing. Each of these probes responds differently to the contents and geometry of the universe. The microwave background encodes conditions when the universe was very young, while supernovae trace the behavior of the expansion at later times. Baryon acoustic oscillations provide a standard ruler in the galaxy distribution and lensing tracks how structures grow. When these independent lines of evidence are combined, they converge on a consistent picture in which dark energy contributes the dominant share of the present energy density and has properties close to those of a cosmological constant. The role of Type 1 supernovae in this picture is to anchor the late-time expansion history with direct distance measurements that are relatively simple to interpret. They provide a way to link the abstract parameters in cosmological models to observable features of explosive stellar deaths in distant galaxies. On a more detailed level, the study of Type 1 supernovae has itself evolved alongside their cosmological use. Improved instruments capture their light curves in multiple wavelengths, track their spectra before and after maximum light, and classify subtle subtypes. These data allow astronomers to refine the standardization process, reduce uncertainties, and explore whether any evolution in supernova properties with redshift could bias cosmological conclusions. So far, while some differences between nearby and distant populations are found, careful modelling indicates that these are not sufficient to overturn the basic finding of acceleration. Instead, they serve as reminders that even tools that appear simple at first can hide complexities that must be mastered to extract precise information about the universe. In the calm framework of modern cosmology Type 1, the supernovae are thus both astrophysical phenomena and cosmological beacons. They mark the endpoints of certain stellar systems while simultaneously tracing the geometry and kinematics of the universe on large scales. Each light curve carries encoded in its rise and decline a measurement of distance that feeds into the reconstruction of the expansion history. When plotted together, hundreds and then thousands of these events draw a clear trend that demands a dark energy component to make sense. This demand does not specify what dark energy is, only that any successful theory must reproduce the observed distance redshift relation. In this way, dying stars in distant galaxies write the influence of dark energy into the observable record. They show that the universe is not only expanding, but doing so in a way that cannot be explained by matter alone, reinforcing the view that a smooth, pervasive dark component is shaping the large-scale future of cosmic evolution, while still keeping its underlying nature hidden from direct view. The cosmic microwave background is a faint glow of radiation that fills the sky in every direction and offers a detailed snapshot of the universe when it's still very young. It originates from a time when the universe is only a few 100,000 years old, long before any stars or galaxies have formed. At that stage, matter and radiation are tightly coupled in a hot, dense plasma made of photons, electrons, and atomic nuclei. Light cannot travel freely because it is constantly scattered by the charged particles. As the universe expands and cools, the plasma gradually recombines into neutral atoms. Once this happens, photons can move almost unhindered through space. The relic radiation from that moment continues to travel until the present, and is seen today as microwave light with a temperature of only a few degrees above absolute zero. Sensitive instruments on satellites and ground-based telescopes map this radiation across the whole sky, finding that it is extremely uniform, with only tiny variations in temperature from place to place. These small fluctuations at the level of tens of microkelvin carry rich information about the contents and geometry of the universe. The cosmic microwave background acts as a screen on which the early universe has written a record of its conditions. Slightly denser regions in the young plasma compress and heat, while slightly less dense regions rarefy and cool. Gravity, pressure, and radiation all interact to drive oscillations in this fluid, similar in spirit to sound waves in air, although occurring on cosmic scales. When recombination happens and photons decouple from matter, these oscillations are frozen into the pattern of temperature fluctuations on the sky. Regions that were compressed appear slightly hotter. Regions that were rarefied appear slightly cooler. By analysing the angular pattern of these fluctuations, cosmologists can infer key properties of the universe, such as how much ordinary matter and dark matter it contains, how curved space is, and how the primordial fluctuations were distributed in size. One way to summarise the pattern is to decompose the sky map into features of different angular scales and measure how much power exists at each scale. The resulting spectrum shows a series of peaks and troughs whose positions and heights depend sensitively on the cosmic ingredients. Dark matter leaves a clear imprint in this pattern. Because dark matter does not interact with radiation in the same way as ordinary matter, it does not take part directly in the pressure-driven oscillations. Instead, it provides additional gravitational wells in which the plasma moves. The amount of dark matter affects how strongly gravity can pull material into denser regions before radiation pressure pushes it back out. This balance shapes the relative heights of the peaks in the temperature power spectrum. By fitting models with different dark matter densities to the observed spectrum, cosmologists can determine how much dark matter is present with high precision. These analyses consistently indicate that dark matter makes up about a quarter of the total energy content of the universe, with ordinary matter contributing only a smaller fraction. The cosmic microwave background therefore confirms, using conditions in the very young universe, the same message that galaxy rotation curves and cluster studies reveal. At later times, most of the matter is dark. Dark energy also influences the microwave background, though in a more indirect way. Its presence affects the overall geometry and expansion history of the universe, between the time when the radiation is released and the moment it is observed. Light from the cosmic microwave background must travel for nearly the entire age of the universe, close to 14 billion years, to reach present-day detectors. During this journey, the expansion history determines how the angular sizes of features on the last scattering surface are projected onto the sky. If the universe contains a significant dark energy component that influences expansion at late times, this will change the apparent scale of the main acoustic peaks. By comparing the observed positions of these peaks with theoretical expectations, cosmologists can measure a combination of parameters that includes the dark energy density. When the microwave background data are combined with other probes, such as baryon acoustic oscillations and supernovae, a consistent picture emerges in which dark energy contributes about 70% of the current energy density, and the overall spatial geometry is very close to flat. The polarization of the cosmic microwave background provides further tests. Polarization arises because the last scattering of photons off electrons has a preferred direction when there are local quadrupole patterns in the radiation field. The resulting polarization pattern can also be decomposed into angular scales and compared with models. It offers an independent way to check the inferred densities of ordinary matter and dark matter, and to probe the ionization history of the universe when the first stars turn on. While dark energy has a more subtle effect on polarization than on the temperature spectrum, precise measurements of both help tighten the constraints on all components. In addition, secondary effects such as the integrated Sachs-Wolf effect, where time-evolving gravitational potentials imprint small additional temperature shifts on the microwave background, provide yet another way to see the influence of dark energy on the growth of structure and the evolution of gravitational wells. Taken together, the observations of the cosmic microwave background show that the dark sector is not a late amendment to cosmological models introduced only to explain recent data. Its influence is already present when the universe is young and uniform, setting the background against which small perturbations grow. Dark matter shapes how those perturbations evolve into the seeds of galaxies and clusters, while dark energy helps determine the overall geometry and the way in which those seeds are projected into the present sky. The precise agreement between different experiments that measure the microwave background, using distinct instruments and observing strategies, strengthens confidence that the general picture is correct. Yet, as with other lines of evidence, the microwave background reveals only how much of each component exists and how it behaves gravitationally. It does not directly identify the microscopic nature of dark matter or the physical origin of dark energy. In this calm but powerful view, the cosmic microwave background functions as a cosmic photograph taken when the universe is still young, one that can be analysed in exquisite detail. Every slight hot or cold spot corresponds to a small variation in density that will later grow into a part of the cosmic web. The precise statistical pattern of these spots tells cosmologists how much dark matter and dark energy the universe contains, and how these components influence the early dynamics of the plasma and the later expansion. The fact that a single sky map can encode such a wealth of information speaks to the coherence of the cosmological model. At the same time, the very success of this model highlights the remaining mystery. Cosmology can state with considerable precision that dark matter and dark energy together dominate the energy budget, and that they affect the formation of structure and the expansion history in specific measured ways. What it still cannot say is what dark matter particles are, or why dark energy has the small but non-zero value implied by the data. The microwave background therefore stands as both a triumph of observational cosmology and a quiet reminder that the deepest questions about the dark sector remain open, inviting further observations and new theoretical ideas to explain the unseen components that have guided the universe from its earliest visible moment until today. The idea that dark energy might be a property of space itself arises naturally once an accelerating universe is accepted as a real feature of cosmology. In general relativity, the equations that relate matter and energy to the curvature of spacetime allow an additional term that behaves like a constant energy density filling all of space. This term is often called the cosmological constant. If it is present, empty space is no longer truly empty. It carries a uniform energy density and an associated pressure that is negative in the sense required to drive accelerated expansion. In such a model, dark energy does not clump or form structures. It does not gather into halos or clouds. Instead, it is spread evenly everywhere, the same in one region as in any other, and its density remains nearly constant as the universe expands. The more space there is, the more total dark energy exists, but the energy per unit volume stays the same. Observationally, this behavior fits well with the evidence so far. The accelerated expansion inferred from supernovae and large-scale structure can be described by a dark energy component whose properties match those of a cosmological constant within current uncertainties. The simplest interpretation is therefore that dark energy is vacuum energy, an intrinsic property of the fabric of space-time. This simple picture leads quickly to a deeper puzzle. In quantum field theory, every field has a ground state, and even in that lowest energy state there are fluctuations. Virtual particles appear and disappear, and the field carries what is called zero-point energy. If all these contributions are summed over all possible modes up to some high-energy cutoff, the resulting vacuum energy density is extremely large. By contrast, the energy density associated with dark energy, as inferred from cosmic acceleration, is very small in ordinary particle physics units. The difference between these two values spans many orders of magnitude. In other words, naive estimates of vacuum energy from quantum field theory overshoot the observed dark energy density by an enormous factor. Reconciling this difference is one of the deepest unsolved problems in theoretical physics. It suggests that either there is an unknown mechanism that cancels almost all of the vacuum energy, leaving only a tiny residue, or that our way of calculating these contributions is incomplete and must be revised. Several broad approaches have been explored to address this tension. One is to accept that dark energy really is a pure cosmological constant, and to search for symmetries or dynamical processes that might set its value to the small observed number. So far, no widely accepted mechanism has been found, although many ideas have been proposed. Another approach is to consider that dark energy might not be perfectly constant, but might arise from a slowly evolving field that changes over cosmic time. In such models, often grouped under the label of quintessence or related concepts, a scalar field permeates space. Its potential energy and kinetic behavior together give rise to an effective dark energy component, whose density and pressure can vary. Depending on the shape of the potential and the initial conditions, the field can mimic a cosmological constant for a period, then diverge from that behavior later. These models introduce new degrees of freedom and parameters, and they must be tuned to match the precise constraints from supernovae, the cosmic microwave background, and large-scale structure. At present, observations do not require such variation, but they also do not fully exclude it, leaving room for gently evolving dark energy as a speculative possibility. A third line of thought considers whether the effect attributed to dark energy might reflect a modification of gravity itself on large scales rather than a new energy component. In these scenarios, the basic equations that relate matter and curvature are changed in a way that reduces to general relativity in regions of high density, and on small scales such as within the solar system, but deviates on cosmic scales where densities are low and the universe is nearly homogeneous. The goal is to produce accelerated expansion as an emergent property of the modified gravity law without adding a separate dark energy fluid. However, any such theory must pass many tests. It must reproduce the successful predictions of general relativity in the solar system in binary pulsars and in the dynamics of galaxies and clusters. It must also match the detailed pattern of the cosmic microwave background and the growth of structure over time. Many modified gravity models struggle to satisfy all of these constraints simultaneously. As a result, while they remain topics of active research, the simplest cosmological constant model continues to provide the baseline description. From a practical standpoint, treating dark energy as vacuum energy has clear consequences for the future of the universe. In a model where the dark energy density remains constant and dominates over matter, the expansion accelerates in a way that approaches exponential growth. Bound structures such as galaxies, clusters, and smaller systems remain intact, held together by their own gravity. However, the distances between these bound structures increase ever more quickly. Over very long timescales beyond the current age of the universe, by large factors, galaxies outside of the local gravitationally bound region will move beyond the horizon defined by the speed of light and the expansion rate. Their light will no longer reach an observer. In such a far future, any remaining observers would see only their local group or cluster, with the rest of the cosmic web stretched beyond causal contact. The universe would appear increasingly empty on large scales, even though dark energy would continue to fill space uniformly. If dark energy instead evolves slowly, the long-term picture could be somewhat different. A dark energy density that decreases over time might allow the expansion to approach a more gentle behavior in the far future, though not enough to bring about a global recollapse if the current trends continue. A dark energy density that grows stronger could in more extreme models lead to scenarios in which even bound structures are eventually overcome by expansion. Such outcomes depend sensitively on the equation of state and its possible time variation. At present, the data favour a model close to a constant dark energy, and more exotic options remain speculative. Future surveys that map the expansion history and the growth of structure with greater precision may reveal small departures from a strict cosmological constant behaviour, or they may tighten the evidence for constancy even further. Despite these uncertainties, one feature remains robust in the calm summary that cosmology currently offers. Whatever dark energy is, whether pure vacuum energy, a slowly rolling field, or a sign of modified gravity, it acts today as a nearly uniform background that does not clump, exerts negative effective pressure, and drives the accelerated expansion of space. It is not localized in particular regions, but appears as a property of the universe as a whole. Its presence is felt not in laboratories or small-scale experiments, but in the way distant galaxies recede in the subtle shifts of the cosmic microwave background and in the pattern of structures across billions of light years. The concept of dark energy as energy of space provides a useful working description that meshes with these observations and offers a starting point for deeper theories. At the same time, the huge gap between simple quantum estimates of vacuum energy and the tiny value inferred from cosmic acceleration stands as a clear sign that some important piece of the underlying physics is missing or misunderstood. This gap keeps dark energy firmly in the category of known effects, with unknown origins, a quiet but powerful influence on the universe, whose simple mathematical form hides a complex and unresolved physical story. In the search to understand why the universe accelerates, and how unseen mass-shaped structure cosmology does not stop at the simple picture of cold dark matter plus a cosmological constant. Alongside that baseline, many researchers explore more flexible ideas in which the dark sector is dynamic rather than static, or in which the law of gravity itself changes on large scales. These alternatives are not adopted because the standard model fails to match observations. Instead, they are investigated because the underlying physics of dark matter and dark energy remains unknown, and because the simplest descriptions leave major theoretical questions unanswered. If the vacuum energy really is responsible for cosmic acceleration, its tiny value compared with naive quantum estimates demands an explanation. If dark matter is made of particles, their nature has so far escaped detection. In this space of partial knowledge, dynamic fields and modified gravities offer possible ways to link the observed behavior of the universe to deeper mechanisms that might emerge from particle physics or new theories of space-time. One broad class of ideas replaces a strictly constant dark energy with a slowly evolving field often imagined as a scalar field that fills space. In these models, sometimes grouped under names such as quintessence or related concepts, the field has a potential energy landscape that guides how it rolls over cosmic time. When the potential energy dominates over the kinetic part, the field can act very much like a cosmological constant, producing negative effective pressure and driving accelerated expansion. As the field evolves, its energy density and pressure can change, altering the rate of expansion. The equation of state parameter which connects pressure and energy density can in principle vary with time rather than staying fixed. Observationally, this would leave subtle signatures in the way the expansion history and the growth of structure respond to dark energy. Surveys that measure supernova distances, baryon acoustic oscillation scales, and weak lensing patterns therefore work together to constrain how much room there is for such evolution. So far, the data are consistent with very little or no time variation, but they still allow a range of gently changing models. In this sense, dynamic dark energy remains a live possibility, one that could eventually reveal itself if future measurements find small departures from the constant case. Other field-based ideas consider dark energy that interacts with matter or with dark matter in ways that differ from simple gravity. For example, some models introduce coupled dark energy, in which the scalar field exchanges energy or momentum with dark matter. This can change how dark matter clusters and how structures grow, leading to different patterns in the cosmic web and in the cluster population. To remain viable, such interactions must be weak enough not to violate existing constraints, yet strong enough to have observable consequences on large scales. There are also models where scalar fields adapt their behavior depending on the local environment, becoming light and active in low-density regions, but heavy and nearly inert in high-density ones. These screening mechanisms are designed to hide new forces in laboratories and the solar system, while allowing them to influence cosmic expansion. They show how flexible the theoretical landscape can be when trying to reconcile new fields with stringent experimental tests of gravity in familiar settings. Beyond dynamic dark energy, some proposals shift attention to gravity itself. General relativity has passed many precise tests in the solar system and in strong field regimes near compact objects, but these tests mostly probe scales far smaller than the distances between galaxies. It is therefore natural to ask whether gravity might behave differently on cosmological scales. Modified gravity theories take this possibility seriously, changing the relation between matter and curvature in the fundamental equations. Some add new terms that become important when the curvature is low, others introduce extra fields that mediate additional gravitational-like forces, and some embed four-dimensional spacetime in higher dimensional frameworks, where gravity can leak into extra dimensions at large scales. The common aim is to reproduce accelerated expansion without an explicit dark energy fluid, or to offer a different interpretation of what that fluid represents. Any such modification faces a demanding set of observational checks. It must reproduce the success of general relativity, where that theory has been tested directly, such as in the precession of planetary orbits, the timing of binary pulsars, and the behavior of light near massive bodies. It must generate a cosmic expansion history that matches the supernova data and the distance scales inferred from baryon acoustic oscillations. It must also yield a pattern of growth for cosmic structures that agrees with both the cosmic microwave background and present-day maps of galaxies and lensing. These requirements tie together many different phenomena. In some modified gravity models, the same change that produces accelerated expansion also alters how quickly gravitational potentials decay over time. This can leave a clear signature in the integrated Sachs-Wolf effect, or in the way lensing strength evolves with redshift. Precision measurements of these signals can therefore rule out broad classes of theories or restrict their parameters. Another important arena for testing gravity is provided by gravitational waves, the ripples in space-time produced by accelerating masses. The detection of gravitational waves from merging compact objects combined with observations of light from the same events allows astronomers to compare the speed at which gravitational waves propagate with the speed of light. In many modified gravity theories, these speeds differ, especially on cosmic scales. The close match observed in some events severely constrains such deviations, ruling out large parts of the parameter space for models that attempt to explain dark energy through changes in gravity. In this way, gravitational wave astronomy, though still young, has already played a role in shaping which alternative theories remain viable. Dynamic dark matter scenarios form another piece of this speculative landscape. Instead of a single species of cold, collisionless particles, some models propose a richer dark sector with its own forces and interactions analogous to the diversity seen in ordinary matter. In these pictures, dark matter might have multiple components, some of which behave almost like the standard cold scenario, while others interact more strongly, form bound states, or even cool and clump into structures that are difficult to detect electromagnetically. If such complex behavior exists, it could alter the internal density profiles of halos, change how satellites are distributed, or leave imprints in small-scale structure that differ from simple expectations. Present observations of galaxies and clusters place bounds on how much deviation is allowed, but they do not yet exclude all possibilities. Thus, the door remains open for a dark sector that is more than a single simple particle species. In all of these explorations, the guiding principle is to remain anchored in observational data. The standard model with cold dark matter and a cosmological constant provides a compact description that fits a wide array of measurements, so any new framework must at least match its success. Often alternative models are built to solve specific theoretical puzzles, such as the vacuum energy problem, or small discrepancies between different measurements of structure growth. As new data arrive, some of these models are ruled out, others are adjusted, and a few remain consistent with observations, while offering different physical pictures of the dark sector. The process is gradual and careful. There is no single observation yet that demands a departure from the baseline model, but there is also no complete understanding of what dark matter and dark energy are. This combination of empirical success and theoretical incompleteness keeps the field open to dynamic fields and modified gravities as serious if provisional possibilities. From a calm, broad perspective, the exploration of dynamic dark energy, complex dark matter, and modified gravity shows how cosmology moves forward in the face of deep unknowns. The universe clearly requires components that do not shine, and that affect expansion in ways that ordinary matter cannot. Whether these components are best described as new fields, new particles, or new behaviors of gravity is still under study. Observations trace how galaxies move, how light bends, how structures grow, and how space expands, while theory searches for frameworks that can tie these facts to fundamental principles. Dynamic fields and alternative gravities may turn out to be stepping stones guiding thought toward a more complete theory that eventually reduces back to a simple description at large scales. Or they may capture essential aspects of reality that the current baseline has only summarized in effective terms. Until evidence points clearly in one direction, the standard model of cosmology stands as a practical, well-tested account, and these more flexible ideas serve as structured ways to ask what might lie beneath its dark matter and dark energy terms. In this sense, the dark sector remains not only a set of unknown ingredients, but also a space of theoretical possibilities that continues to shape how the evolution of the universe is understood and investigated. The far future of the universe is shaped above all by the balance between dark matter and dark energy. In the present era, dark energy already dominates the overall energy budget, while dark matter supplies most of the gravitating mass that has built structure. Ordinary matter plays a smaller role concentrated in stars, planets, gas clouds, and dust. Radiation, once the main component in the very early universe, now contributes only a tiny share. As time goes on, these proportions change in a way that further strengthens the influence of dark energy. Matter, both dark and ordinary, becomes more dilute as the universe expands. Its average density falls as the volume grows. By contrast, if dark energy behaves like a cosmological constant, its energy density remains nearly constant per unit volume. This means that as space grows, the total amount of dark energy increases while its density stays about the same. The result is that dark energy's relative importance continues to rise while matter becomes ever less significant on the larger scales. In the near to intermediate future, over timescales of billions of years, structure formation gradually slows. Dark matter continues to dominate the gravitational fields of galaxies, groups, and clusters, and within these bound systems, gravity overwhelms the effect of dark energy. Stars orbit their galactic centers, galaxies move within clusters, and gas follows the local potential wells. New small structures may still form through residual mergers and accretion, but the rate at which fresh large-scale structures appear declines. On scales where gravity is too weak to hold material together against the background expansion, the accelerated growth of space stretches distances faster than matter can collapse. Regions that are not already bound become effectively frozen in their separation. In this phase, dark matter's role shifts from building new structures to maintaining existing ones. Halos that have already formed keep their identity. Their internal dynamics continue with satellite galaxies orbiting, and sometimes merging stars moving through the gravitational field and central black holes accreting whatever gas remains. Inside galaxies, the supply of cold gas available for star formation decreases. Much of the gas has already been turned into stars or has been heated and expelled by stellar winds, supernova explosions, and feedback from active galactic nuclei. Star formation rates, which reached higher values in the earlier universe, decline. Over long timescales, existing stars age and evolve. Massive stars live short lives and end as neutron stars or black holes, while lower mass stars shine dimly for trillions of years before eventually fading. As star formation dwindles, the light output of galaxies changes, shifting toward longer-lived cooler stars and then slowly declining. Dark matter halos remain as the primary mass components, but the luminous content inside them becomes progressively less active. Meanwhile, the accelerated expansion driven by dark energy changes the large-scale environment. Groups and clusters that are currently bound remain gravitationally intact, but the distances between these bound islands grow. Galaxies that are not gravitationally tied to a group or cluster drift farther away in comoving distance, and the expansion speed between them increases. If dark energy is a true cosmological constant, this acceleration approaches a steady exponential behavior. In such a regime, there exists a horizon beyond which events can never influence a given observer, because space expands between them too rapidly for light to bridge the gap. Over timescales much longer than the current cosmic age, more and more of the distant universe passes beyond this horizon. Light emitted from galaxies that are presently visible eventually can no longer reach the local region. In this picture, the cosmic web on the larger scale slowly thins from the point of view of any one bound structure. The underlying dark matter filaments that once connected groups and clusters across hundreds of millions of light years are stretched by the accelerated expansion. While they remain part of the global solution of the equations, their causal influence on a given cluster decreases as horizons form. For an observer living in a far future epoch inside a bound system, such as a large cluster, the view of the universe would be much more restricted. Only the local collection of galaxies and their combined dark halo would remain visible. The cosmic microwave background would be redshifted to such long wavelengths and low temperatures that it would be difficult to detect. Distant galaxies that now trace the large-scale structure would have faded beyond the edge defined by the accelerated expansion. From that vantage point, reconstructing the full story of cosmic evolution and the role of dark energy would be more challenging, because many of the key observational clues would have slipped out of view. Dark matter continues to influence the internal future of bound structures. Over long timescales, the orbits of stars and dark matter particles are altered by gravitational encounters and collective effects. In dense regions, dynamical processes tend to move energy around, gradually driving some material to more extended orbits and bringing other material toward the center. Central black holes may grow slowly by consuming stars and gas that lose energy and sink inward. In clusters, galaxies may merge into larger systems, gradually simplifying the visible population. Throughout this evolution, the dark halo provides the main gravitational well within which these changes occur. Although individual particles move and interactions redistribute energy, the total mass in dark matter within the bound region remains nearly fixed. It continues to hold the structure together, even as the luminous components fade and rearrange. If dark energy behaves differently from a pure cosmological constant, the far future could take other forms. In models where dark energy density slowly decreases its influence, might weaken over time, potentially allowing matter to regain relative importance. In such scenarios, the expansion could approach a more gentle, almost coasting behavior, though current measurements leave little room for dramatic changes without conflicting with the observed past and present. In more extreme models, where dark energy density increases over time, the acceleration could become so strong that even bound systems are eventually unbound. In such a so-called Big Rip scenario, the scale factor grows so rapidly that first clusters, then galaxies, then even smaller structures are disrupted as the expansion overwhelms their internal gravity or binding forces. This outcome depends sensitively on the equation of state of dark energy and its possible evolution. Observations at present favour a value close to that of a cosmological constant, which does not lead to such a violent end, but the possibility of modest departures keeps these scenarios in the realm of careful speculation. Across all these possibilities, one feature is common. The long-term direction of the universe is governed by what dark energy does. Dark matter, though dominant in mass within structures, cannot reverse accelerated expansion on the largest scales once dark energy is taken over. It can maintain and shape local systems, set the internal dynamics of halos, and keep galaxies and clusters intact. Dark energy as a nearly uniform background component with negative effective pressure determines how space behaves when averaged over vast distances. Its precise nature decides whether the universe tends toward a state of accelerating expansion that continues indefinitely, a slower growth where acceleration weakens, or a more dramatic outcome where expansion tears structures apart. From the calm perspective of present-day cosmology, the most likely future under current data is a universe that continues to expand at an accelerating rate, set by a nearly constant dark energy density. In such a universe, the contribution of dark matter to large-scale gravity slowly becomes less important compared with the background dark energy, even as it remains crucial inside bound halos. The observable universe from any one location shrinks in the sense that fewer distant systems remain within the horizon. Over enormous timescales, stars exhaust their fuel, galaxies grow quieter, and the sky changes in character. Yet the dark sector remains active in its own way. Dark matter continues to define the skeleton of bound structures, and dark energy continues to stretch the fabric of space. The interplay between these two unseen components which has already guided the universe from its earliest visible stages to the present network of galaxies, thus also writes the outline of its distant future. The detailed microphysical stories behind them remain unknown, but their combined effect on cosmic evolution from early growth of structure to long-term fate stands as one of the clearest large-scale facts that modern cosmology can describe. In the early 21st century, the picture of a universe dominated by dark matter and dark energy is well established, yet the map of this dark sector remains incomplete. Observations from many telescopes and experiments define where dark matter must be and how dark energy must act, but the underlying ingredients and mechanisms are still unknown. Cosmology now moves in two directions at once. On one side, it refines and extends measurements that describe the dark sector in ever greater detail. On the other, it pushes toward theories that might link these effective descriptions to specific particles fields or modifications of gravity. The result is an ongoing effort in which data and ideas continually test one another, gradually tightening the space of possibilities without yet selecting a single definitive answer. Large sky surveys provide one of the main tools for mapping the dark sector. Wide-field optical and infrared observatories scan broad regions measuring shapes, colours and redshifts for hundreds of millions of galaxies. From these data, astronomers build three-dimensional maps of the cosmic web, trace the pattern of baryon acoustic oscillations and extract weak gravitational lensing signals that reveal the underlying mass distribution. Repeated observations of the same regions allow the growth of structure to be measured over cosmic time, connecting the patterns seen in the nearby universe to that imprinted in the cosmic microwave background. Dedicated space missions and ground-based projects aim to reduce statistical uncertainties, control systematic errors, and cover more of the sky, all with the goal of turning the broad outline of the dark matter and dark energy distribution into a sharper, more detailed map. Alongside these surveys, targeted observations focus on particular systems that provide especially clear tests. Massive galaxy clusters that act as strong gravitational lenses yield fine-scale reconstructions of dark matter, halos including their substructure. Colliding clusters in which gas galaxies and dark matter separate from each other offer constraints on how strongly dark matter particles can interact. Dwarf galaxies with extreme mass-to-light ratios test the behavior of dark matter on small scales and challenge models that predict too many or too few such systems. Precise timing of pulsars in binary systems and networks of pulsars across the galaxy probe gravity in both strong field and weak field regimes, looking for deviations that could signal modified gravity rather than or in addition to dark energy. Each of these observational efforts adds one more piece to the map of how unseen components behave in different environments. Particle physics experiments provide a complementary approach starting from the smallest scales rather than the largest. Underground detectors respond to the inferred local density of dark matter by searching for scattering events between hypothetical particles and atomic nuclei. Collider experiments attempt to produce dark sector particles in high-energy collisions and infer their presence from missing energy and momentum. Dedicated axion and axion-like searches explore the possibility that dark matter consists of extremely light particles that can convert to photons in the presence of magnetic fields or resonant cavities. So far, these experiments have not confirmed a specific dark matter candidate, but they have ruled out wide ranges of parameter space, narrowing the set of viable models. This process is gradual but cumulative. Each non-detection eliminates some combinations of mass and interaction strength, pushing candidate theories toward more constrained and sometimes more subtle regions. Together with astrophysical bounds, these constraints shape the emerging map of what dark matter could be. On the theoretical side, work proceeds along multiple lines to connect the effective cosmological description to fundamental physics. Some researchers look for ways to embed dark matter and dark energy into extensions of the standard model of particle physics, adding new symmetries, particles, or interactions that might naturally yield a stable dark matter candidate or a small vacuum energy. Others explore higher dimensional or quantum gravity frameworks, where the dark sector might emerge from geometric or holographic principles rather than from familiar fields. In parallel, modified gravity theories continue to be refined with screening mechanisms and other devices designed to reconcile new large-scale behaviors with stringent small-scale tests. In all of these avenues, cosmology plays a central role by providing the boundary conditions that any successful theory must meet. Models that cannot reproduce the observed expansion history, the cosmic microwave background pattern, the large-scale structure and the internal dynamics of galaxies and clusters are set aside while those that survive remain under close scrutiny as new data arrive. Future observations are expected to add further layers to this process. More sensitive weak lensing surveys will trace the dark matter distribution with higher resolution testing, whether its clustering matches the simple, cold, dark matter scenario on all accessible scales, or whether small deviations indicate additional physics. Improved measurements of baryon acoustic oscillations and redshift space distortions will trace the expansion history and the growth rate of structure constraining, whether dark energy behaves exactly like a cosmological constant or shows hints of evolution. High-precision studies of the cosmic microwave background polarization combined with maps of large-scale structure will tighten the constraints on the dark sector's contribution to geometry and growth. At the same time, continued searches in laboratories and underground facilities will push further into unexplored ranges of particle properties, while new gravitational wave detections will test gravity in regimes and distances not previously accessible. Despite this expanding effort, it is possible that the dark sector will remain stubbornly indirect, known primarily through gravity, rather than through direct detection of its constituents. It may be that dark matter particles interact so weakly with ordinary matter that only their collective gravitational effects can ever be measured. It may be that dark energy reflects a property of space-time that cannot be isolated in any local experiment. Or it may be that new experimental techniques not yet fully developed will eventually reveal clear signals. At present, cosmology accepts that the dark sector is required to explain a wide range of phenomena, while recognizing that its detailed nature is still open. In this calm assessment, the universe is understood as a system whose large-scale behavior is dominated by components that have been mapped in outline but not yet identified in detail. The luminous matter that forms stars, planets, and living organisms occupies a small corner of this map. Dark matter outlines the skeleton of structure guiding galaxy formation and stabilizing clusters. Dark energy sets the overall pace of expansion and shapes the distant future. Observations across the electromagnetic spectrum from radio waves to gamma rays, together with gravitational waves and particle experiments, continue to refine how these components act. Each new survey detector or theoretical idea adds another contour line to the map of the dark sector, revealing where explanations are robust and where gaps remain. The result is a picture that is both precise and incomplete. Cosmology can track how dark matter and dark energy influence rotation curves, lensing arcs, supernova, light curves, cosmic background patterns, and the large-scale flow of galaxies. It can quantify their relative contributions to the energy budget and describe their gravitational effects over most of cosmic history. Yet it cannot yet say what dark matter particles are made of or why dark energy has the value that it does. The map shows the reach and shape of the dark sector's influence, but not the full nature of the terrain. This state of partial understanding defines the current frontier. The dark components of the universe are no longer vague ideas added to rescue failing models. They are measured, structured elements of a successful description whose deeper origin is still unknown. In that sense, dark matter and dark energy are not only influences that act on the universe, but also questions built into its fabric, guiding present research and shaping how the story of cosmic evolution is told and explored.